to see done off of that?
Yeah.
But can we do like a really, really, really quick review of just like the derivative looks like this is what the normal one would look like. Like I sort of vaguely remembered.
Graphing
Graph the function from the derivative?
Yeah.
Boy, you're telling me you were here, so I was like,
Constantly.
it's fine. Okay, yeah, real quickly. So this is going to be f prime, and we're going to get f from it. So this is a graph of f prime. And we're going to say f is continuous. And it's more interesting to try to make it be continuous.
Yeah.
So I'll say, so we'll go circle, circle, Okay, so there's f prime, and you come up with y equals f of x.
Hold on, I need a second. And drawing.
You want to walk through, you want a moment?
Could we walk through it?
Yeah. So we'll take it, no, it's fine. So if the derivative is 1, what does that make the original function? It's a line with slope 1. Okay, we don't know anything about the y-intercept, so we're free to do it whatever we want. So I think I'll just start it here for no particular reason. And I'm going to go up 1 over 1, so there is my line there so far. Now I'm going to jump to this piece. What's this going to be? So negative 1. Now, I said the original function is continuous. Since the derivative is undefined there because of those open circles, that means we must have a corner point. Okay, so the slope positive 1 connects to a slope negative 1. Now you could put this with any, there's no y scaling here, so you can put way up here, way down here, anywhere in between. Okay, now, what's happening here? Exactly. And you know that it's going to have you can think of one of a couple ways. You say it's got a slope of positive, which means it's going to have to be a parabola that opens up, as opposed to if it came down here, be a parabola that opened down. Or you could think of it as, you know, these derivatives are negative, so it's going to be decreasing, 0, increasing. Now, it's continuous, so I got to connect it to here, but it's going to be a corner point. So I'm going to go something like that. Okay?
So since there's like no scale on it, could I have made my parabola thingy above the x-axis?
As long as it's connected to where you left off. Because remember we said the function has to be continuous. So you can't have a break in your graph.
Okay.
But you could have had all of this slid up or all of this slid down. But you can't have any discontinuities there.
Okay. So like what if I just wanted the like little parabola piece above the x-axis?
Then you just got to adjust what the rest of it does.
I have to move the rest of it too?
It's got to be connected.
Isn't the line that, or the derivative line is increasing the whole time?
So remember, this is the derivative. So the derivative is negative here because it's below the x-axis. So the tangent lines are going to be negative in there.
Gotcha.
It's going It'll be 0 right at the origin, and then it's going to switch to positive. Is that okay?
Yeah.
Okay, so another break means another corner point. Now it looks like the slope, now you got a little bit of estimation and a little bit of leeway because you can interpret it somewhat differently. Does that look like it's a 0 slope or a little bit positive to you because it's your problem, Karen? Right to the right of that open circle.
It looks a bit positive.
Okay, so then I'm going to make it be, well, that's fine. So then we're going to come out of here a little bit positive. But it's going to be a corner point either way. Now it's going to get to be bigger and bigger positives. So it's going to, and it's also, so you have vertical asymptote, which means we're thinking now, because the function is continuous, this is going to have to come from either a vertical tangent or a cusp. How do you know which is which?
Would it be a cusp in this case?
Well, you had a 50-50 chance.
Oh.
Chose wrong. Because they go to the same infinity, that's going to make it be a vertical tangent. Over here, you're going to see one that goes to different infinities.
So that would be
That's going to be the cusp.
There we go.
We'll see. Okay, so here it's going to come up here, and then we're going to have that vertical tangent right there, and then it's going to come up out of there. Okay? Now it's going to go till we get a slope of 0. So I'm going to have to make this thing round off and the horizontal tangent right there. That makes sense? Now we're going to switch to negative derivative. So now it's going to have to start decreasing. And it's going to continue decreasing until now we said here, since this is going to different infinities, you can see that the slope of the tangent line here is going to fall off the cliff from the negative side. That's what's happening there. But then it's going to jump right back up to positive infinity on the other side. So that means it's going to be very steep, right up in there, coming out of there. So that's why the cusp gives you different vertical asymptote with different infinities. Okay? Now it's going to, it looks like the derivative is going to stay positive but get closer and closer to 0. So our function is going to do what?
Well, the slope stays positive, so the function is just going to keep increasing, right?
But it's going to approach some kind of horizontal asymptote. Okay, so it's going to do something like that.
Thank you. That helps.
Good, good. Lot to digest. Yeah.
So I know the first bit when we had a straight line, you were like giving us the actual slope of the line. For everything else, can we just kind of put what we want for the slope as long as it's the right direction and cavity?
And sometimes, yes, to answer your question, yes. And sometimes there may not be tick marks. And so the best you can say is that's going to be positive, so the line's got to be rising. And this is going to be negative, so it's got to be falling. And you have the artistic license to make it however steep you want. When it's actually marked, then you have stricter guidelines you have to follow. I know. Like
So-
coloring inside the lines either, I know.
A problem that was similar to this one that I had trouble with was it was another one where you were given F prime, you had to graph F, but it wasn't all like cool and funky like this one, it just looked like this.
Mhm.
And I don't know how to do that.
Okay. So none of that craziness here, just a basic.
Just like kind of like an X cube, but with some like extra like.
Well, let's put a few twists in.
Yeah.
And this is our
F prime.
prime. Okay, it's been a while since we've talked about these.
Yes.
So we're going to try to come up with y equals f of x. And again, you know, you guys know, because we've done a lot of integration already, when you integrate a function, you're going to get that plus c. So whatever we have could be translated up or down and still be correct. So there's no holding you to any particular y value at any particular place. So you have that kind of freedom. But the shape is not so negotiable. That's going to have to be, I mean, there's a little bit of room, but, you know, where our function is increasing, yours should be increasing. and so on. So what I would do first is, let's see where this derivative is equal to 0. So we're looking for relative mins and maxes to start with. So we have a place right here, and a place right here, and a place right here, where the derivative is equal to 0. So at this place, on the left the derivative is positive, and on the right it's negative. So that means this must correspond to a relative max. Okay, so I'm just going to say relative max. And how about here? It's negative on the left, but then negative again on the right. Do you remember what that is? It's called a shelf point. So I'm going to say that's going to be a shelf point. And here goes negative to positive, and so that's going to be a relative mean. Now, you remember what happens at these relative maxes and mins on the derivative, what that means in terms of the original function f? No, that would be if we're going the other way. So if that was f and we were getting f prime, that would be an x-intercept. Going the other way, do you remember what that is? Midpoint? Somebody had it. It's going to be an inflection point. So what we're saying is that you know, if you think about this is our derivative, it's positive. So our original function is increasing, and it's increasing faster and faster and faster to this point. So that means our function is getting steeper and steeper and steeper until it gets to this point. And then it's going to continue to be positive, but it's not going to be increasing as fast. So these relative mins and maxes in the derivative are going to be inflection points, or POIs, in our original function. So I think it's kind of nice to sort of know that in advance and then kind of go from there. Okay. Now again, no scaling, so you can start this adventure anywhere you like. Our derivative over here is a little bit positive, but very close to 0. So that means what's happening over here in our original function. Increasing, but probably coming off of maybe an asymptote or something like that. So I don't know. I'm going to start here. I'm going to start increasing until I get to a point of inflection right there. And I'm going to make that, I'm going to communicate that I intend that to be an inflection point because I've seen some of your graphs, and telling where it goes from concave up to concave down is not always crystal clear. So you might indicate that by making that a clear point. Then it's going to keep increasing but change concavity until we get to this maximum, relative maximum. Is that okay? Sure? Okay. Lacey? Now we're going to start to decrease until we get to this point of inflection. So it's going to come down there, and now I'm going to change from concave down to concave up. And I'm going to do that until I get to this shelf point. So that looks like it wants to be a relative minimum, but it never quite makes that commitment and goes to increasing. So after decreasing gently here, like it's going to turn and go up, it turns and dives back down. So it's going to continue decreasing until we get to this point of inflection. Okay? Okay? If I start going too fast, let me know. So now I'm going to keep going down, but now I'm changed from concave down to concave up until I hit where that relative minimum I said was going to be down there. And then it's now increasing, so I'm taking off until I get to about where the x value of that inflection point is going to be. And it's going to turn over and be concave down, and it's going to continue increasing but approach 0. So like we've seen before, it looks like it's approaching some kind of horizontal asymptote there. That help? Okay. Anything else? This is what I want to do. I mean, I'm going to teach you stuff I've taught you before. So if there's things that are fuzzy or not clear, we can spend the time on that, and we'll get where we get. And if you need more help, go visit again, or you can check the supplemental videos as well. And I think a lot of what we're doing today is stuff that you probably remember better because we've done a lot with it. I hope. So we're talking about 3.3. These are the rules for differentiation. So we remember the derivative of a constant is 0. We remember our power rule. The derivative of x to the n is very nice. We've done a lot of that over the time in between. We know that the derivative of a constant times a function is the constant times the derivative of a function. And we know the derivative of the sum or difference of two functions is the sum or difference of their derivatives. Which means we can find the derivative of any kind of polynomial-like function. This isn't actually polynomial, but we have 4x to the 5th minus, let's say 1 over x plus 3 times the cube root of x squared plus pi times x plus x to the e minus pi to the e power. We can find the derivative of this. Give me a moment.
Is that x to the e or x to the z?
X to the e. Euler's number e is what I had in mind. Is that okay? And that's pi to the e at the end. All right, derivative of 4x to the 5th. Really lonely up here for a moment, thank you. 1 over x we're thinking of as x to the negative 1 in a derivative friendly form. So that's going to become positive x to the negative 2 or positive 1 over x squared either way. And we're thinking of this as x to the 2/3. So when we differentiate that, we're going to get 2/3 x. Very nice. And the derivative of pi times x. And the derivative of x to the e. X to the e minus 1. And the derivative of minus pi to the e. 0 because that's a constant. Okay. We have our product rule. Love these days. I wanted to be a conductor. So we say the derivative of f of x times g of x is the first times the derivative of the second plus the times first times derivative of the second, plus second times derivative of the first.
It's all coming back to me.
It all comes back. These are warm memories. Not like that other stuff. Maybe, sort of. You can admit it. We had fun. The quotient rule, well, I should name it. This is our quotient rule. Today we differentiate two functions that are being divided. So should we say it first? You want to start with a denominator. Denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Oh. So it's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. Some people like to shorten it up a lot and say denominator times derivative of the numerator times numerator times the derivative of the denominator squared. I don't know if you like that or not. There's a cute little saying, but I never remember it, so it doesn't do me much good. Something about high D low or D, I don't know what it is. I'm not that clever. Okay. Anyway, let's see, how am I doing? We got that. Let's do higher order derivatives, we know. So I think we just want to make sure we understand, especially the Leibniz notation. So higher order derivatives. So we kind of have this competing notation, or there's lots and lots of notations. So if we say y equals f of x, there's our original function, then we can denote the first derivative by f prime of x. That's sometimes called prime notation. It's more suggestive of a function. You can also use, when we say dy dx, that's called Leibniz notation, because Leibniz, one of the co-creators along with Newton of calculus, came up with that notation. You could also call it y prime. You'll sometimes see that as the derivative of the function f with respect to x. These are all equivalent notations. You'll see it written like you're taking the derivative of something. So this is how you show kind of like the operation of differentiating. You say d dx or differentiate with respect to x. Did I miss any? I think that's pretty much it. Then after this, we can take a second derivative, which we can denote as f double prime of x. And then you write it as d squared y over dx squared. So you sometimes call it the second derivative of y with respect to x twice. So the 2's go in slightly different places there. So that's just another notation for second derivative.
So if you put the 2's in the same place, does that have a meaning? Is that another definition?
I don't think so. I think it's just like a typo or a misspelling or something like that. So
I'm just curious.
yeah, no, good question. And we should also say, I mean, it's easier to denote how you evaluate a derivative at a number using the prime notation, but it's kind of awkward this way. It's typically, you would do something like that. So you're saying take that derivative, and this is how you show the evaluation at x equals 5 piece. And then likewise, we can do this, f triple prime is the third derivative, and third derivative with respect to x 3 times. Just keep adding exponents. Then the fourth derivative, once we get above 3, we don't use tick marks anymore. So you'll see it written with that parentheses 4. And then it'll be still, I mean, the dy dx notation doesn't change. You just keep bumping up the exponent 1.
Did you use Roman numerals instead of switching to?
I don't think that's generally accepted. So I don't think, and I think it would be too confusing. I guess 1 would be fine, and 2 and 3 would be, yeah, I guess they would, but it's not done. So I'm not sure how that would be interpreted. We can talk about velocity and rates of change. So 3.4, velocity, and other rates of change. So when we say rate of change, so kind of a difference from your AP prep days, when we say rate of change, we mean instantaneous rate of change. So we will have to say specifically when we mean an average rate of change. So if we don't, then the understanding is it's an instantaneous rate of change. And you do that even when, you know, the independent variable is not time. So still a rate of change, even if there's no time involved in the context of the problem at all. Let's see. So motion on a line, do a lot of this. So this is a big AP topic where our motion is always going to be either usually like on a horizontal line or a vertical line. And so we will talk about something like, you know, the position at time t, or oftentimes s of t. And so we know then that the first derivative is our velocity. Oh, I just found a new one too. This just came up on this electronic discussion board. The second derivative is acceleration. And I can't imagine that you would ever be asked to find anything beyond the second derivative of position. But curiously enough, the third derivative is known as the jerk, which I like to refer to as the Hogshead function, not referring to Macy in any sense. But I found that the fourth derivative, actually, I heard this. This was the one I hadn't heard before. It came up, that's called the snap. And I don't know what use that is, but it's the snap. Yes.
If you leave off the parentheses on the 4 when you're writing the fourth derivative, would that be considered incorrect?
That is definitely not correct, because then that's going to be interpreted as s of t to the fourth power.
So why not just put confusion in either of those?
Why not what?
Why not use Roman numerals then?
You know, I'll take that up with the calculus committee.
Okay.
I'll appreciate it. I'll set a problem.
I'll get back to you on that. So we also know that speed, now what we are going to also do at BC topic, we're going to do position in 2 dimensions once we do parametrics. And so then we'll talk about a velocity as a vector and acceleration as a vector. And speed still is the absolute value of the velocity. So velocity has a sign associated with it. It can be positive or negative, but speed is always positive or 0. And shall we just real quick derive our position function when we shoot something in the air? So we know that acceleration due to gravity, if we use the metric system, is going to be negative 9.8 meters per second squared. And so then that means that the velocity, and if we say our velocity, say at time 0, is v sub 0, and our position at time 0 is s sub 0, then it's really just a big differential equation that we can solve. And so we know that we can integrate here. I'll do the left side. The integral of s double prime is s prime. You integrate the right side. The integral of negative 9.8 is, with respect to t, if that helps, negative 9.8 t plus c. We plug in v of 0 equals v sub 0, so v sub 0 is c, so we get s of prime of t is negative 9.8 t plus Piece of 0, we integrate again and get position. And that's going to be the integral of t is t squared over 2, so you get negative 4.9 t squared. Piece of 0 t plus c, the constant, which is going to be, when you plug in 0, your s sub 0. Thank you for your patience. Good question. I like it when you ask questions.
Can I go another review?
Yes.
Avoid using the.
Oh, yeah.
You're definitely getting it.
Yeah. Did you say what time it starts?
I forgot that. I saw it with me, but it's so cool. Yeah. Forgot that.
I asked for this food, let me try it.
Oh,
Yeah.
Thanks.
Oh, I love
Oh, I'm like,
8 o'clock Friday.
yeah, we'll get it.
Are you coming to study family? Yeah, sure.
Yeah.
Thank you.
Yes.
All right, we'll be on there.
Oh, that's so unusual. So you can figure out when you want to.
Yeah, can we come in during the lunch tomorrow? What time is that?
7:30 should be like
All right.
Oh, I thought that was next week. That's all right.
Yeah. Also, and I have to in the back of the room, back to get you back.
Yeah, I might do that.
I might do that, because occasionally I do get drafted.
It's hard to, yeah.
It's hard to take notes, it's hard to do anything when you're drafting.
Yeah.
Standing up gets rid of it.
Yes.
Have a good day.
Great to see you, Tom.
Yeah. What?
These are new protocols.
Yeah, I was trying to do it, and I was like, yeah.
You're like, math? What is that? Like that, barely, and I so peaceful. I'm broken, I have a cushion behind my back. Right now, so I'm wearing the hoodie and walking around with the hoodie, and I'm sure people are
You can never have too many hoodies.
ain't that the truth? There's no such thing as too many hoodies.
So I'm gonna have you work on a review problem online. I got some housekeeping to keep track of. I gotta upload a video, I gotta take attendance, all that stuff. Rather than you sitting around and waiting for.
Riley Mountain Brown, please come to the main office. Riley Mountain Brown, please come to the main office.
So the purple is f of x. And see if you can figure out how to graph y equals f5 of x. That make sense what I'm asking you to do? And if anybody feels bold enough to come work on the board here or on the back, you're welcome to do that as well. And then, like I said, I've got some, gotta come early to get the good seats, Tanner.
I know, it's just like,
Got aced out. It's like coming to church late. You gotta sit in that front row.
Old people always take the front row quickly in my church.
Is that right?
Yeah,